Okay, so thanks so much for coming to our talk today, our first breakout session. I'm Mathieu Millard. I'm a staff software developer at Unity. I'm based in Montreal, and I'm part of the UI group at Unity.
And I'm Esther Ugolini, a senior software developer with a focus on quality, also part of the UI group at Unity. So today we'll be introducing you to the UI Toolkit Test Framework. But before we get into that, we want to share some information with you. The UI Toolkit teams at Unity have a pretty hefty suite of UI, unit, and integration tests that run on several different platforms in the editor and at runtime. If you've never done any UI testing before, you might not know this, but UI automated tests are historically difficult to write, debug, stabilize, and they can take a really long time to run. So we've developed this UI test framework to try and improve the UI test experience, both for Unity developers, but also for game developers. Within the UI Toolkit teams at Unity, we have continuous integration, also called CI, jobs that run all the automated tests for that team on every PR they open. One of the UI Toolkit teams integrated UI test framework into their existing tests. And in doing so, they saw faster test execution times and more stable tests. We'll cover why UI automated tests might suffer from instability a little bit later in the presentation. For users like you, and even for UI Toolkit developers, writing automated UI tests was often a difficult task. Now, using UI test framework, you'll be able to more easily write UI automated tests for UI Toolkit UI.
So let's see what we're planning for you today. We'll start by giving you a rundown of the difficulties around UI automated testing. Since there are a few different testing frameworks that exist already, we'll do a quick refresher of what those frameworks are and how they differ from the UI test framework. We'll then introduce you to the UI test framework briefly, and we'll illustrate its features later via some code samples. We've got a bagel game to use as a demo for this presentation. It shows off some of the new features from UI Toolkit. And then we'll learn about the UI test framework by looking at some example in the context of that bagel game. So there are a couple of different factors that play into UI automated testing being historically difficult. One of the most obvious factors is the large variation between platforms. Like, different devices will have different screen sizes, different resolution, different DPIs, different system fonts, or other platform-specific differences that will make UI tests harder to write and especially harder to maintain. Another factor is the amount of async operations. Assigning a value somewhere, but having to wait for a while for that value to be reflected visually. Tasks that happen in parallel or in a nonlinear fashion, like keyboard or mouse events. Animations, data loading and synchronization, especially across a network, are all other examples of this, and they can be unreliable and make it hard to predict the state of your UI at any time. That results in several timing issues that especially affect automated tests. Tests may need to wait for a frame for these operations to complete, but it's not always sufficient, as there is rarely any guarantee that any operations will have completed while your test is stalling its execution. There's also a difference between editor frames and runtime frames, since the editor update loop and the player loop are different. Some UI can also be timing dependent. For example, clicking on an icon in the project browser and having it enabled for renaming, let's say. As a result of these timing issues, UI automated tests takes much longer to run, as they have to wait for all these operations to complete. that affects your test run both locally and on your CI. All of these issues essentially amount to the unfortunate reality that UI automated testing has a pretty steep learning curve. You have to be aware of all of these issues and sometimes even knowing about the internal workings of the features you're trying to test. So now let's see what tools we can add to our belts to tackle these challenges.
So we'll start by doing a quick refresher on NUnit and Unity Test Framework so that you can have the full context for the rest of this presentation. So NUnit is an open source unit testing library for .NET languages. Among one of its many features is the ability to add test-related attributes to your code. A test attribute is itself a bit of code. You can see them in the screenshot here, surrounded by square brackets, that allows you to perform certain operations or give code certain capabilities. NUnit will invoke the method assigned to the test attribute at the appropriate time, if applicable. For example, this setup attribute indicates that the mySetup method should be run before every test belonging to this test class. And the test attribute indicates that my first test is a test. Unity Test Framework, which is different from UI Test Framework, is a package that facilitates automated testing for Unity projects. You can use Unity Test Framework to write tests for your edit mode or play mode code, and you can execute those tests in the test runner window via command line or via code. Unity Test Framework integrates a custom version of NUnit, and it extends it with certain Unity-specific capabilities. For example, allowing you to interact with the player or editor loop during tests. Unity Test Framework provides the Unity Test attribute, shown here, which allows you to write tests that will execute over multiple frames. The Unity Test attribute must be applied to a test that is of type IEnumerator. This type indicates that the function will perform some yield return action, meaning that it will pause its test execution, perform that action, and then resume the test execution. This is an example of a Unity-specific capability provided by Unity Test Framework that allows you to wait for one frame in your test. Whereas this is an example of waiting for a domain reload to occur. And yet another example where we're waiting for 1 second in real time. Unity Test Framework allows you to create tests for edit mode or play mode. Edit mode tests run inside the editor, meaning that they can depend on editor-only things like editor windows or custom inspectors, for example. When tests are located in an editor test assembly, they're considered edit mode tests. Play mode tests, on the other hand, run in play mode in the editor or at runtime. They're a bit more limited, but they represent basically the same environment as your developed game. So let's now briefly introduce UI Toolkit Test Framework, also called UI Test Framework for short. It's a package shipped with Unity 6.3 onwards, so you can start using it for your projects right now. UI Test Framework doesn't overwrite the functionality provided by NUnit or Unity Test Framework. It works alongside it. So then, what is UI Test Framework exactly? It's essentially a collection of APIs called the UI test fixtures. The test fixtures are basically base classes that you can inherit from to give your test greater control over its UI. They'll do things like automatically manage the lifetime of UI Toolkit internals for you. But more on that in a few minutes, where we'll learn from some examples.
It's now almost time to see some code. But first, let me introduce our Bagel game demo. All examples we'll use for this presentation are from our Bagel game. In this game, you control a bagel that must navigate through a set of obstacles to reach its goal, the toaster. The game showcases some of the new features coming in UI Toolkit. For starters, well-spaced UI. As you can see, there are some UI within the 3D space, and there's also some bagel stats that follow our bagel object through the world. We've added some flair to our UI by adding blur USS filters to menus that are not in the currently active focus. These menu buttons are more stylized thanks to custom UI shaders that add this cool gradient here. And you can zoom in as much as you like on these icons because they are defined with SVG. So they look amazingly smooth, no matter how big or small. The demo also showcases the UI Test Framework, and we'll dive into some automated tests written for the game UI, both in play mode and edit mode. We'll provide a link to the project at the end of this presentation. And you can also see the project live at the 2D and UI booth in the exhibition floor.
Okay, let's talk a little bit more about what you can do with the UI test fixtures. You can do a couple of things. One of them is you get the ability to simulate UI interactions by sending events. On the right-hand side here is a little diagram that explains an abstracted view of what happens when I click on some UI Toolkit UI. So we're going to walk through it. If we start from the top, if I click on some UI Toolkit UI with my computer mouse, let's say, my operating system, in this case Windows, will send a pointer down event to Unity. Unity will receive that event and forward it to UI Toolkit. Then UI Toolkit will either handle the event itself or allow user code to handle it. We mentioned this just to say that UI Test Framework operates at the level of this blue bottommost box here. So we bypass the operating system level, but we're also bypassing the level where Unity receives the event and sends it to UI Toolkit. That means UI Test Framework has the ability to send events directly to UI Toolkit. You might be wondering what kind of information is contained in an event. If we use the same example, UI Toolkit probably needs to know where I clicked in my UI, or what mouse button I used for my click, or if I had any keys held down while I clicked, for example. The second ability that you unlock with the UI test fixtures is the ability to skip the uncertainty of waiting for time or frames in your test by gaining direct control over the UI Toolkit update loop. Let's look at our first test example. So even bagels need a break sometimes, so our game has a pause menu. So we've written a test to click on the resume button of this pause menu and verify that it gets correctly actioned. Let's walk through step by step. So starting at the top, we have our first introduction to a UI test fixture, and that is the aptly named UI test fixture class. As we mentioned, the test fixtures are base classes that you can inherit from in your tests. When you inherit from UI test fixture, your tests will be provided with a panel. But the type of panel that will automatically be created for you depends on whether your test is in edit mode or play mode. In this case, you can't tell from the screenshot, but this is a play mode test. So our test fixture will have access to a runtime panel. The panel that the test fixture instantiates is empty, but you will be able to set it up. You can set up the UI within your panel by accessing the root visual element property of the UI test fixture. This root visual element property is a visual element like any other, so you can add elements to it, or as we're doing here, use the clone tree function to load our pause screen UXML directly into the panel. We now introduce another one of the UI test fixture's key APIs, and that is the panel simulator object that is accessible by the simulate property. The simulate property represents the simulated panel. For now, we'll just say that that refers to the panel that is tracked and managed by the UI test fixture. Since we just set up our UI in the previous steps, we call simulate.frameUpdate here, which is another very important API, to ensure that our UI is laid out properly. We'll learn more about frameUpdate and the concept of a simulated panel in a few minutes. Next, we query for the button that we're interested in testing. So in this case, it's the resume button. And we set its clicked functionality to flip a Boolean if it is triggered. Finally, we use the simulate property again to send a click with this click API. There's a few different variations of the click method. This one takes a visual element and will send a click to the world-bound center of that element. Just as an aside, it's generally bad practice, especially in UI automated tests, to hard code coordinates. we always recommend sending coordinates relative to elements so that your test is more robust. For example, maybe we could have successfully written this test by sending a click to a vector of 10, 10. But if ever we move our resume button or we resize our window, all of our UI tests will break, which is pretty disastrous. So we've implemented this best practice into some of the UI test fixtures functionality. It's also worth noting that although you can provide a visual element to this click API, it will only use it to locate the position for the click. That is to say, if you had another element in front of this button, it's possible that your click would not make it to the button. Once we've sent our click, we perform another simulate.frame update. This is a good practice to do, since if you're validating a response of your UI to an action, you can be assured that it will have executed after a frame update. This function essentially replaces the need to yield frames or wait for your UI to update. And finally, we perform our assertion. I'll be a little bit particular here and just mention that it's also usually a best practice to include an assertion message when you perform assertions. We've omitted them from this presentation because we need to maximize our slide real estate.
So once you've completed the game, you can add your name and your high score to a leaderboard. So this screen contains a text field to input your name. So to write a test for this, you'll need to use the panel simulator typing text method. So let's have a look. So using the same kind of setups that we had in our previous test, we instantiate our game over screen. In this test, since we want to validate text typing, we need, in order for keyboard events to be dispatched to this element, we need to give our text input, our text field, the focus. So we do that here, and then we call frame update to make sure that our UI is ready for action. Then we call the typing text method on the panel simulator, providing the text that we want to type. And finally, perform a frame update before doing our validation. The typing text method takes in a string and will send all the required events to simulate the typing action, again, abstracting all the differences between platforms. So on some platforms, sometimes you need as many as like 3 events for each key that is pressed. So this method takes care of all of that for you. The only thing you need to do beforehand is to make sure that you give the keyboard focus to the element that you wish that will receive the keyboard events, basically.
Okay, that was probably a lot of information, so let's do a quick recap. We just introduced the first UI test fixture, the aptly named UI test fixture class, that you can use as a base class for your tests. When you inherit from the UI test fixture, your test will have access to an empty panel, but you can set up the UI in the panel by using the root visual element property. You also get another really important property when you inherit from the test fixtures, and that is the simulate property. This will be one of your go-to properties when performing UI interactions. As we saw in the last few examples, you can use the simulate property to perform a click and provide an element whose position you want to click on, or you can use the simulate property to type text with the typing text method. The simulate property also gives you access to controlling the UI toolkit update loop. So whenever you need your UI to be up to date, you can call simulate.frameUpdate instead of waiting real frames.
So we've talked a bit about the frame update method. Now let's peek under the hood at what actually is happening when we call that frame update method during our test. So when an editor window is created or a UI document component is enabled at runtime, it will create a hierarchy of elements that will get picked up by a UI Toolkit panel. That UI Toolkit panel will then own that hierarchy of elements and will manage rendering, event dispatching, and keyboard focus for that hierarchy. It contains what we're calling updaters. It's a collection of subsystems that track all the changes made to your visual element hierarchy and perform all the computation that are necessary for that hierarchy to be rendered on screen. So in a typical frame, event processing is triggered by either the input system or the native editor window management layer. With the UI test fixtures, this is triggered by the event simulation calls like the simulate.click that we saw earlier. The frame update function forces the panel to execute the rest of the UI toolkit loop and handle all of its side effects that end up invoking user code. So the panel first invokes any scheduled calls that are due. It will then run data bindings and update all the transitions animations for you. In the editor, these happen at regular interval independently of the main editor update loop. So this often leads to instabilities in your tests, since you can't really be sure that any particular step will have run if you wait for 1 frame, let's say, or 2 frames, or even 10 frames, right? When a repaint event occurs, the panel runs the remaining update steps. That is updating the styles that might be out of date, computing layout, transforms, and then generating the meshes that end up being rendered on screen. So calling frame update will eliminate all the guesswork, and you can be sure that everything is up to date and run properly before you make your validations and tests.
Okay, let's take a look at another example, again with the pause menu, but for a different button this time. Our pause menu has this long press button to restart the game, but it doesn't cause the game to restart right away. Users need to click and hold on it for 1 second. While the user is click and holding on the button, it fills up with this like loading bar styling to let the user know approximately how much longer they need to click and hold the button. Let's look at how we might write this test using some of the facilities offered by the original Unity test framework. First, I'll point out that we're using Unity test here. Since we know that our button has a hold time, we know we'll need to wait for some amount of time, so we need to use the Unity test attribute. Next, we create our long press button, and we add it to the root visual element. To write a test for this, we actually need to separate the click action into its click down and click up actions. A single click consists of 2 events, the first being a pointer down event that is sent when I, for example, click down on my mouse button, and the second being a pointer up event that is sent when I, for example, release the mouse button. Here, we're sending a regular click just to make sure that that's not enough to activate our button's functionality. And here, we're sending just the pointer down using this mouse down API to the button's position. If you remember earlier when we showed some basics of Unity test framework, we showed an example of waiting for a certain amount of time. So we're using that same API here to wait for the button's hold time, which is 1 second. Then we call our frame update function, and we validate that our button was correctly actioned. While this works, you might find that timing issues cause it to be unstable on your local PC. You might be tempted to add a few other yield return nulls to get an extra frame in there, but what might work locally for you might not work the same on a coworker's machine or in your automated CI. It's also worth pointing out that because of how we've written this test, we're actually waiting for at least 1 second, which means that our test will take at least 1 second to run. A second seems like a short amount of time, but it really accumulates as you get more tests. So let's see how we can improve the situation using the UI test fixtures. You'll notice here that we're actually using the test attribute. So this means that when we use the UI test fixtures, we can write this whole scenario without yielding 1 frame. So this is the only other difference in this test. When we have a simulated panel, we have complete control over the time value that is seen by UI Toolkit scheduled calls and animations. In this case, we're replacing the wait for seconds real time with our frame update call. But this time, we're providing a value to the frame update function. This means that we'll be advancing the time that is tracked by the panel of the test by that specified amount instantly. We don't need to wait in real time, and a test that used to take 1 second to run now executes almost instantaneously. This would also enable us to test boundary conditions that can be tricky to test sometimes, or allow us to validate elements going through transition animations, for example. So if you need to check that something happens at a specific time, you can absolutely do so with the frame update function.
So let's do a quick recap. So the simulate.click function sends both a pointer down event followed by a pointer up event. In that test, we needed to have a bit more fine-tuned control, so we opted for the mouse down event. Right? There are plenty of other event simulation functions available to you that we unfortunately won't have time to cover today. The frame update function ensures that UI Toolkit has run the entire update loop on the arc of your hierarchy of elements. And that includes the scheduler, styling, layouting, data bindings, and transition animations. When used by UI test fixtures, UI Toolkit doesn't use real time. The frame update function, in addition of running the update loop, also advances a fake time value that is tracked by that panel. So if you provide no time, it will increase by a default amount that is configurable. But if you provide that time value, it will use that time value instead. Other methods will let you reset the current time or query its value. The UI test frameworks also come with some additional functionality that you can use along with your test fixtures classes. They're called UI test components, or test components for short. The test components also have functionality that is tied to the test lifecycle, meaning that they would automatically perform certain actions before and after each test. The UI test framework comes with a few components built in, but you can easily create your own to define reusable functionality that you can share between your test fixtures. If you're familiar with NUnit, you might see the similarity with the test action attributes. These gets us to the same goal, but gives us a bit more control around where they're activated and when those lifetime methods get invoked. So now let's see how to use them. So we'll see the first example of this here. If you remember, we have this long press button that triggers only after a delay. It displays that progress bar when pressed. So in this test, we'll want to verify that the long press button hold functionality correctly apply custom style values to our progress bar. So let's learn how to do this using the styles applicator component. So to use any test component, you first need to add it to your test fixture using the add test component method and providing the type of your component. Here we keep a reference to that component so that we can reuse its functionality later. So exactly as we've seen so far, we create a long press button and add it to our root visual element. Here we also query for the progress bar. We'll want to validate that the styling is correctly applied on that element when we press the button. So now we can use the styles applicator. So using the reference from before, we call add styles to element. This method dynamically creates a style sheet and adds it to the visual element. So after applying that style, we need to frame update so that everything is computed and perform our validation, checking that the background color was properly applied to our timer progress element. So as I mentioned, test components have functionality that is tied to the lifecycle of your tests. So at the end of the test, the styles applicator will automatically remove any style that was added to a visual element and will also destroy the dynamically style sheet object that was created. So you can add styles to element and don't worry about cleaning everything up at the end of the test.
Okay, let's go back to our bagel for a second. The bagel has some UI attached to it that shows its stats as it tumbles towards the toaster. On the right-hand side is its toppings count, in this case, sesame seeds. And it's really tough being a bagel, so you can see that its toppings decrease as it takes damage from the world around it. We wrote a test to check that these toppings updated accordingly. Since the toppings are controlled via data bindings, we'll need to rely on the frame update function to test this. Let's walk through it. We're still inheriting from a UI test fixture here, so we need to set up our UI in the empty panel that the test fixture gives us. This is just a little bit more involved this time because we need to connect data bindings to the scriptable object that we're creating here. We're also introducing another test component here, and that is the cleanup util component. This component allows you to add objects to be automatically destroyed or disposed at the end of your test. This step shows us loading the UXML for just the right-hand pane of the bagel tracker stats UI into our root visual element. Then we hook up the bindings to the bagel tracker scriptable object that we created earlier. And we fetch the bagel toppings progress bar that we'll use for validation. And finally, we directly set the toppings count that we want to check on our scriptable object. In order to correctly test this, a simulate frame update is required. That's because data bindings, as Mathieu mentioned, are updated as part of the UI Toolkit update loop asynchronously. As you know, frame update allows you to gain control over the UI Toolkit update loop. So you don't have to wait for things to happen or deal with the uncertainty of asynchronous operations. You can make them happen immediately. So we perform our frame update, and then we can safely do our validation to check that the toppings in the UI has updated to the value that we set on our scriptable object.
So our UI also includes a settings window that has a dropdown that allows you to pick a different theme to style your UI. So now let's go through a test that checks that selection for this dropdown, which when clicked, pops a drop-down menu to allow you to select the theme. So here we're introducing a new component called the pop-up menu simulator. So as usual, we add the component to the test fixture, and we'll use it later in this test. So setting up our UI, we query for the dropdown, and then we'll use that dropdown to fetch the input field that we then click on. So using the menu simulator still requires you to click on elements in order for them to invoke the menu pop-up functionality, right? Now comes the usage of this element, of the menu simulator. So after we click, we can validate that the menu was actually displayed as the result of that click event, right? Then we use the menu simulator to also select a menu item in order to switch the dark theme. Now, you might be wondering why we cannot actually use clicks here. Well, under the hood, like the drop-down menu implementation varies widely between different platforms. So inside an editor, the pop-up menu uses the operating system's menu, which can't be really clicked on programmatically or easily inspected, right? At runtime, they will use standard visual elements, so that's a bit simpler. On Windows, for instance, popping a drop-down menu actually steals the focus from the main editor window and will pause the execution of NUnit. So obviously, that's not the most nice thing for automated tests, right? So here, we're calling the simulate menu selection to simulate the selection of the option we want to test. And we then validate that the drop-down properly reflects that selection. So we've now introduced you to the concept of UI test components. So these features can unlock functionality when you use any of the test fixtures. So to use them, you simply need to add them to your test using the add test component function in the test code. So the first test component we saw, the styles applicator, allows you to easily add styles to element, and it will take care of cleaning everything for you afterwards. Another useful test component is the cleanup util component, which automatically disposes or destroys any objects assigned to it at the end of each test. And at last, the pop-up menu simulator component, which enables you testing pop-up menus by bypassing the operating system rendering of these pop-ups that could eventually pause the execution of your automated tests, right? So one of the appeal of UI Toolkit is the fact that runtime UI can also run inside the editor, right? And most editor UI can also run inside the player. So let's look at how you can leverage the UI test fixtures to reuse your test code between runtime and editor.
Okay, so we'll look at an editor test for the pause menu. If you remember in our previous examples, we wrote several tests for the pause screen at runtime. So this bit of code here at the top is actually the test from the previous example. It's the pause screen test at runtime. We've just kind of spliced the code together here a bit visually to illustrate our point. But this top section would originally be in a runtime test assembly, and this bottom section, which is new, is a pause screen test editor that would be in an editor test assembly. And what we're showing here is that the pause screen test in the editor actually inherits from the pause screen test at runtime. So you can actually reuse the same code and the same test that you wrote for runtime in the editor, meaning you can run the tests in both environments without duplicating your code. You won't need to add any code to the pause screen test editor. The pause screen test at runtime will execute on a runtime panel. The pause screen test in the editor will execute on an editor panel. We also touched earlier on the concept of a simulated panel that you can access with a simulate property. In the editor context, the simulated panel means that a panel exists without being attached to an editor window, which is something impossible to achieve normally. This separation, though, allows tests to execute more quickly because the UI doesn't need to render. But what does that actually mean? That means that while your editor UI tests that inherit from the UI test fixture base class are running, you won't see any UI on the screen. This is beneficial because the tests will run much faster when we don't need to create an editor window. It might seem like a small thing, but it really adds up over thousands of tests. In case you were wondering, though, we do provide some functionality to aid with debugging or writing tests, since, as you might imagine, it can be difficult to write a UI test with no UI. Let's look at another example, though. So this next example is for what we're calling the Bagel All UI window, though in hindsight, we really should have called it the Everything Bagel window. Sucks. It's basically an editor window with every UI from the game within it. So there's a giant scroll view, and we have all of our UIs in this one window. And it kind of provides an easier and more straightforward way to review our UI. In this test class, we're inheriting from a new test fixture this time, and that's the editor window UI test fixture. This test fixture sets up the test with a reference to an actual editor window, whose type gets provided as a parameter to the fixture. Here, we're using the editor window UI test fixture, so our Bagel All UI window will be instantiated directly by the fixture. We won't need to do any additional setup like we had to for the UI test fixture tests. Here, our root visual element property will already be populated by the content of our Bagel All UI window. It was possible to use the UI test fixture class in those previous tests because our UI was easily set up in parts. If you remember, we just created a long press button or connected just one part of our data bindings. The editor window UI test fixture is ideal to use if your UI would not be easily set up in parts, or if your UI relies on logic declared in your custom editor window. The downside would be that Unity has to go through the creation of your editor window, so your tests will take a little bit longer to run. So we're creating our test fixture. It's the editor window UI test fixture, and we're providing our Bagel all UI window. So that means the test fixture will spawn a window of that type and hook it up for simulation. Since we mentioned in the previous example that you can't really see your UI during tests that use UI test fixture, I want to mention that you will see your UI by default when you use the editor window UI test fixture, since it spawns a real editor window and not a panel that's not attached to a window. In this test, even though we're using a real editor window, sometimes the test can execute quite quickly. So if we want to visualize our UI, we can activate debug mode. That means that the window will stay open for debugging when a test fails. You can also activate debug mode in a UI test fixture test, and that just means that your panel will be wrapped in an editor window and displayed when the test fails. Next, as usual, we perform our simulate frame update so that our UI is ready for action. And finally, we click on our main menu's leaderboard button. This test has been trimmed down a bit for simplicity, but it's worth noting that if you wanted to interact with the leaderboard later on in the test, you'd have to make sure that it's visible, since if you remember, our leaderboard was at the bottom of this scroll view. As we mentioned earlier, when we perform UI interactions by sending events, we send them to the position of elements, not directly to the elements themselves.
So let's look at our final example for our in-game pause menu. So this time, we're using yet another test fixture, the runtime UI test fixture. So far, we've mostly seen usage of the base UI test fixture, which spawn an empty panel to be populated by you in the test. The runtime test fixture would be the appropriate one to use if we needed to load a scene for testing, or if our test relies on some logic running in our mono behaviors. So that's what we're doing here. We're loading our scene. Then we do need to wait for the scene and some other operations to load. So frame update will only remove the need to wait for the UI toolkit loop. So if some operations still rely on the player loop, they will still need to be returning the execution flow to the player loop by using coroutines with that yield return. Once we have our scene set up and loaded, we query for the UI document via the game objects and components in our scene. And then using the set UI content function, we let the runtime UI test fixture take the UI document and the UI contained in it and hook it up for simulation. Now here in our test, after fetching our setting buttons and our setting pane, we can verify that after we set the proper player state, when we click on our settings button, then the settings pane becomes visible. Let's do a final recap. So UI test fixtures come in different flavors. The UI test fixture class can be used as a base class for both editor and runtime tests. Depending in which context is used, it will set up your test with either a runtime panel or an editor panel sitting in background. The editor window UI test fixture will spawn your custom editor window and enable you to run your test alongside that window. The runtime UI test fixture allows you to load your scene content or prefabs, then simulate on the panel used by the UI document you provide. So if your UI can be decoupled from the logic of your editor window or your scene components, the UI test fixture is the one to use. Otherwise, you can use either the two other ones for your tests. You can activate debug mode to render your UI on screen and pause execution if a test fails. So inside an edit mode test, it will display your editor window and prevent further changes made by additional test case by forcefully failing them. So your UI will be pristine and you'll be able to debug it, inspect it using the UI Toolkit debugger. In play mode, it will pause execution, allowing you again to use a UI Toolkit debugger to inspect the state of your test. Then pressing that play button in the main toolbar will resume execution of your remaining test cases.
So to conclude, you can start using UI Test Framework for testing your UI Toolkit UI, beginning in Unity 6.3. So make use of the test fixtures like UI Test Fixture, Editor Window UI Test Fixture, or the Runtime UI Test Fixture to reliably and efficiently test your UI. Simulate UI interactions like clicking and typing, and more that we weren't able to cover in this presentation. And use the UI test components to unlock additional functionality, like being able to test pop-up menus. If you've ever avoided or struggled with UI automated testing before, please give UI Test Framework a try and let us know what you think.
So again, thank you so much for coming today. So you can access the UI Toolkit, the UI Test Framework documentation with the QR code on the left, or fetch the Bagel Game Unity project from the repo on the right. So thank you very much.